In a matter of seconds, the siding surrounding the porch light begins to move as it hums against the darkness. Not a single bug, not 10. Tens of thousands of them enter attics and wall cavities as hundreds, then thousands, climb up through spaces, little bigger than a credit card. Eventually, whole farmhouses throughout Pennsylvania appear to breathe with a changing shield-shaped skin. Homeowners wake to find them dropping from ceiling fans. Families vacuum them by the cupful, only for more to arrive by morning. Nobody called them here. Nobody can explain, at first, why they keep coming back to the exact same houses, year after year, like they're returning to something. That single image, repeating in kitchens and barns across the eastern seaboard every autumn, is the opening scene of one of the strangest ecological detective stories in modern American agriculture. Because the insects gathering on those walls are only the visible half of the invasion. The other half is happening in silence, inside fruit that looks perfect from the outside. Cut an apple in half in an orchard near Adams County, Pennsylvania, and you might find it hollow with corky brown scarring beneath unbroken skin. The tree looked healthy, the harvest looked normal, but something has been feeding from within, and the damage isn't visible until it's too late to sell the crop. By the time growers across the mid-Atlantic started noticing the pattern, in the early 2000s, they weren't just losing a few bushels. Entire orchard blocks were being downgraded to juice-grade fruit, worth a fraction of fresh market prices, and nobody could say for certain what was causing it. This is where the mystery begins, and where we takes you into the heart of one of the costliest and most misunderstood insect invasions in American history. Hidden away in packing materials or shipping containers, bound for the Allentown, Pennsylvania area, a new arrival slipped into the United States completely unnoticed sometime in the 1990s. The creature responsible has a name that sounds almost formal for something so destructive. Haliomorpha hullis, the brown marmorated stink bug. Native to East Asia, including China, Japan, Taiwan, and the Korean peninsula, nobody photographed its landing or sounded an alarm. It simply appeared, shifting quickly from a mere curiosity to a nuisance, and finally to something closer to a catastrophe. By 1998, the first confirmed specimens were being collected in Allentown. Within 5 years, the insect had been found in New Jersey. Within a decade, it had colonized more than a dozen states. Today, it has been confirmed in over 44 states across the country, from the orchards of Oregon to the vineyards of Virginia, feeding on more than 170 different plant species: apples, peaches, pears, tomatoes, peppers, soybeans, and even ornamental trees that homeowners plant for shade. Beyond the bruised fruit, a staggering economic wound was opened by the pest, particularly during the historic outbreak year of 2010. That year, Mid-Atlantic apple growers alone reported losses exceeding $37 million, highlighting a crisis that cut far deeper than ruined harvests. The insect feeds by piercing plant tissue with its needle-like mouthparts, leaving behind dimpled, discolored patches known as cat-facing that render apples, peaches, and pears unsellable at retail, even when the fruit is otherwise edible. Packing houses in Pennsylvania, Maryland, and West Virginia culled entire bins of produce that season, and some orchards saw damage rates climb above 50% of their crop. Peppers and tomatoes developed cloudy, corky lesions beneath the skin. Soybean fields in the Mid-Atlantic and Midwest suffered shriveled, discolored seeds that cut yields and dockage grades at the elevator. Multiply that across a decade of spread, dozens of affected crops, and an expanding range, and one widely cited estimate puts the brown marmorated stink bug's potential toll to American agriculture at $20 billion in losses, a staggering figure that places this single insect among the costliest invasive species in the nation's modern farming history, and a small but telling slice of the roughly $120 billion the United States loses each year to invasive species overall. And still, farmers kept losing the fight. That's the part of the story that should unsettle you. This isn't a tale about an unstoppable monster winning through raw power. Stink bugs aren't fast. They aren't strong. They don't even bite people. What makes this insect so dangerous is something far stranger. It appears to have already found a way around nearly every tool humans throw at it. Insecticides, the first and most obvious weapon, tell the story well. Broad-spectrum sprays can knock down stink bug populations in an orchard for a matter of days, but the insects are highly mobile, flying in from surrounding woodlots, hedgerows, and even suburban yards in waves that field scouts still struggle to predict. Spraying more often only escalates the cost per acre, while devastating the very insects that used to keep other orchard pests in check. Within a few seasons of heavy stink bug spraying in mid-Atlantic apple orchards, researchers documented secondary pest outbreaks. Aphids and mites resurging because the natural predators that once controlled them had been wiped out by the same chemicals meant to stop the stink bugs. The cure was making the disease worse. Pheromone traps looked like a smarter idea. Scientists identified an aggregation pheromone that draws stink bugs together, and growers hoped a well-placed trap could pull the insects away from valuable crops. Instead, in some cases, the traps worked too well, drawing in even more stink bugs than were previously present in a given orchard block, essentially advertising a dinner bell to every stink bug within flying range. Exclusion netting helped protect individual trees, but proved far too costly to deploy across hundreds of acres. Every solution solved one piece of the puzzle while opening a new one elsewhere. It was around this time that a Pennsylvania grower, call him Tom Becker, a third-generation orchardist whose family had been growing apples near Adams County since his grandfather planted the first rows after the Second World War, began keeping his own private log of what he was seeing. Tom wasn't a scientist, but he had spent his whole life reading an orchard the way other people read weather, and what he was reading now didn't make sense. He noticed the insects didn't spread evenly. They clustered on certain trees near the woodline, ignored others entirely, and seemed to time their invasions of his farmhouse to the very week the nights turned cold, as though following some calendar only they could see. He noticed that killing large numbers with pesticide sprays sometimes made the following year's population worse, not better. He noticed that some seasons, his losses tracked less with how many stink bugs he saw, and more with something happening elsewhere entirely. In the fence rows, in the nearby woods, in patterns he couldn't observe from his own fields. Tom's frustration, echoed by hundreds of growers across the region, eventually reached the desk of Dr. Tracy Lesky, an entomologist with the USDA Agricultural Research Service, and one of the leading stink bug researchers in the world. Lesky and her colleagues had been tracking the invasion since its earliest years, and what she found, piece by piece, over the following decade, reframed the entire crisis. The stink bug wasn't simply resilient, it was, in evolutionary terms, unopposed. In its native range across Asia, Haliomorpha halis exists in a landscape shaped by millions of years of coevolution, with its own predators, parasites, and competitors. A web of natural checks that keeps its populations from spiraling out of control. In North America, it had arrived into an ecological vacuum. None of the continent's native predators recognized it as prey. None of its natural enemies had made the crossing with it. It was, in effect, an unguarded species walking into an unguarded landscape, and every human intervention, every spray, every trap, was only a temporary patch on a problem rooted in evolutionary history, not simply agricultural science. This is where the documentary's search for a hero begins, and where it leads audiences somewhere they don't expect. Long before the stink bug crisis, one insect had already earned a reputation in American gardens and farms as the ultimate natural predator, the praying mantis. For nearly a century, gardening catalogs and farm supply stores have sold mantis egg cases, promising customers a chemical-free solution to pest problems. And on paper, the praying mantis is an extraordinary hunter. It has stereoscopic vision, allowing it to judge distance with startling precision. Its head can rotate nearly 180 degrees, tracking prey other predators would lose. Its forelegs, lined with sharp spines, snap forward in a strike that takes a fraction of a second, often too fast for the human eye to fully register. Watching a mantis hunt on camera, it's easy to believe you're looking at nature's perfect assassin, and easy to believe this was the answer American orchards had been waiting for. For a while, that belief held. Farmers and gardeners released mantis egg cases by the thousands, hoping to build an army of ambush predators that would quietly patrol crops and consume the stink bugs, decimating their yields. But the deeper researchers looked, the more the story shifted. Praying mantises are not specialists. They are opportunistic generalists, striking at nearly anything that moves within range and fits in their grasp. Stink bugs, when they do end up in a mantis's diet, are only a small and incidental part of it. Far more often, mantises take bees, butterflies, and other pollinators essential to the very crops farmers were trying to protect. Field observations have even documented mantises capturing small frogs, lizards, and, in a discovery that startled the entomological community when it was first documented and published, hummingbirds ambushed at backyard feeders. A predator marketed as a farmer's ally was, in practice, an indiscriminate hunter with little interest in solving anyone's stink bug problem specifically. Then came the twist that reframed the mantis story entirely. The vast majority of egg cases sold across the United States for the past century haven't even been native species. Chinese mantises and European mantises, both introduced generations ago for pest control, have spread widely across the country, while the native Carolina mantis, smaller, less conspicuous, evolved alongside North America's own insect communities, has quietly declined in numbers across much of its range. Today, several state conservation programs actively encourage residents to search hedgerows and dried plant stalks each winter, identify the larger foam-like egg cases of the invasive mantises, and destroy them before they hatch. The insect once marketed as the ultimate biological control had become, in its own right, an invasive species competing with and displacing native wildlife. What could solve the stink bug crisis if the continent's most famous predator couldn't? From the stink bug's own evolutionary homeland, rather than American soil, came a surprising answer, delivered not by a larger predator, but by a smaller one. It finally emerged from the very last place most people would have thought to look. In the forests of Eastern Asia, researchers surveying native Haliomorpha hales populations had long known about a tiny parasitoid wasp barely large enough to see without magnification. Trisulcus japonicus, which came to be known by a name suited to its precision, the samurai wasp. Measuring a mere 1 to 2 millimeters in length, scarcely the size of a sesame seed, this microscopic powerhouse possesses an evolutionary toolkit specifically engineered to dismantle the brown marmorated stink bug, BMSB population at its source. Unlike a mantis, the samurai wasp never touches an adult stink bug. Instead, the female wasp utilizes highly sensitive chemical receptors in her antennae to track the scent of adult stink bugs and the defensive compounds they leave on foliage. Once she locates a freshly laid cluster of stink bug eggs, typically glued in neat, geometric rows of 28 to the undersides of leaves, she begins a meticulous inspection. Using her ovipositor like a surgical needle, she pierces the tough chorion of the stink bug egg and injects her own egg directly inside. But her precision doesn't stop there. After oviposition, the female marks the exterior of the egg with a chemical pheromone to signal to other passing wasps that this cradle is already occupied, maximizing efficiency across the colony. Her larvae develop rapidly within the stink bug egg itself, consuming the host's yolk and developing embryo from the inside out. Over the course of just a few weeks, the wasp larva pupates, transforms, and chews a neat, circular exit hole through the eggshell. Instead of a destructive stink bug nymph emerging to ravage crops, a new adult samurai wasp steps out, ready to mate and begin the cycle anew. Through this quiet warfare, an entire generation of stink bugs can be erased before it ever hatches, without a single adult insect being harmed. It sounds almost too quiet to matter, but in its native range, this wasp is one of the primary reasons Haliomorpha hales never becomes the runaway pest in Asia that it became in the United States. In its introduced North American habitats, the brown marmorated stink bug enjoyed an enemy-free space, multiplying exponentially because local predators like spiders and birds found them unpalatable or inefficient to hunt. In stark contrast, studies conducted in the insect's home range of China, Japan, and the Korean peninsula have found parasitism rates on wild stink bug egg masses reaching into the double digits and, in some surveyed populations, well beyond 50% to 80% of all eggs destroyed before hatching. Because the samurai wasp can produce multiple generations in a single summer, outpacing the reproductive cycle of the stink bug itself, its ability to suppress outbreaks is compounding. It isn't eradication, It's regulation, a ceiling imposed by millions of years of shared evolutionary history, keeping a population in balance rather than eliminating it outright. In 2014, researchers in Beltsville, Maryland, made a discovery that changed the entire trajectory of the American response. While surveying wild stink bug egg masses in the field, not in any laboratory, not through any planned release, scientists found that Trisulcus japonicus was already present on U.S. soil. It had arrived on its own, almost certainly the same way its host once had. Hidden, unnoticed, a stowaway that slipped across the ocean years earlier and had been quietly establishing itself in the landscape long before anyone documented its arrival. This detail is easy to move past too quickly, but it's the discovery at the heart of this entire story. For years, USDA researchers had been working through the lengthy, careful process required before intentionally releasing any non-native biological control agent, testing the samurai wasp against non-target native species to ensure it wouldn't repeat the mistakes of the mantis story. And while that research was still ongoing, nature had already made its own decision. The wasp had found its way to the very ecosystem where its ancient host was already causing chaos, independent of any human release program, following a track laid down by coevolution rather than policy. Since that discovery, Trisulcus japonicus has been confirmed in dozens of states, and field studies conducted over the following decade have tracked rising parasitism rates on wild stink bug egg masses in several regions, a slow but measurable sign that the balance from Asia may be reestablishing itself, insect by insect, egg mass by egg mass, on a new continent. Consider the contrast this creates. Federal and state agencies have spent tens of millions of dollars over the past 2 decades on stink bug research, monitoring networks, and management programs, and individual growers spend hundreds of dollars per acre every season on insecticide applications, trying to hold the line. Meanwhile, a wasp smaller than a grain of rice, requiring no funding, no infrastructure, and no human oversight, may be quietly doing more to stabilize the crisis than any single program devised in a laboratory. It's not that the human effort was wasted, the research building today's understanding depended entirely on it. It's that the most effective long-term solution turned out to be one nature had already written, evolved over millions of years in a different hemisphere, waiting to be recognized rather than invented. Zoom out far enough, and the stink bug crisis stops being a story about one insect at all. It becomes a story about a pattern humans keep repeating. Confronted with an ecological problem, the instinct is almost always to look for a single powerful fix, a stronger chemical, a fiercer predator, a simpler solution that can be deployed and forgotten. Pesticides suppressed stink bugs while collapsing the populations of native insects that had been providing pest control for free. Mantises were sold as an ecological cure, while becoming an ecological complication of their own. Each fix addressed a fragment of the problem, while quietly generating another one, because none of them accounted for the web of relationships an ecosystem actually depends on. What the samurai wasp represents isn't a bigger hammer. It's a reminder that healthy ecosystems are not run by the single most dominant organism in them, but by countless relationships, refined over unthinkable stretches of time, each one calibrated to a specific counterpart through a process no laboratory can replicate on a human timescale. For thousands of years, long before apples were ever grown in Pennsylvania, this wasp and this stink bug were already locked in their quiet, evolutionary negotiation on the other side of the world. America's crisis wasn't a failure of that relationship, it was simply what happens when one half of it is left behind. Every autumn, stink bugs still gather on farmhouse walls, proving that this story is far from over. Tom Becker still checks his trees every September with the same wary eye his grandfather once used. And this year's harvest, like every harvest for the past 2 decades, will carry some measure of damage. No spray program has fully solved. Meanwhile, researchers are still tracking the samurai wasp spread and measuring parasitism rates field by field, still uncertain exactly how far this natural rebalancing will go or how long it will take. Nature rarely resolves these stories with a clean ending, and this one is no exception. But somewhere among the leaves of an orchard in the mid-Atlantic, right now, a female wasp barely visible to the naked eye is searching the underside of a leaf for a cluster of eggs left behind by an insect that crossed an ocean 30 years ago. She has no idea she is the answer to a multi-billion-dollar agricultural crisis. She is only doing what her ancestors did for millions of years before her, on a continent that had forgotten to bring her along the first time. That is the story this crisis keeps trying to tell us, if we're willing to listen. The biggest predator was never the point. The oldest relationship was. And as long as farmers keep checking their trees each fall, and researchers keep counting eggs beneath the leaves, that relationship is still being written, one generation at a time. If you want to follow where this story goes next, because it is still unfolding, right now, in orchards you'll never see, and forests half a world away, subscribe to our channel, and stay for what nature does when no one is watching.